Yes, uh, good evening, one and all. I hope you can see the screen. So let us go to the topic of uh, this AC and DC power circuits, that is real, reactive, and apparent power. Okay, so real, reactive, and apparent power. Okay, so these three kind of powers are available. So and moreover, so these are denoted by P, and reactive power is denoted by Q, and apparent power is denoted by S. So this real power, so which is the actual power required by the load. So real power is the actual power required by the load. So and it is stored, or it is it is being absorbed in the form of heat. Okay, in case of a resistive load, right? So and coming for this reactive power. Okay, so the reactive power is neither generated nor absorbed. Okay, so and the line itself, it is being created because of the reactive elements in the line, that is XL or XC, so which is called as inductive reactance or capacitive reactance. Okay, so this property of heat, the absorption in the form of heat, is observed only in resistive element, okay, which is denoted by R. Okay, coming for this apparent power, so it is used to define the actual rating of the machine, and the units are VA. Coming for this reactive power, the units are VAR. So here you can see, so the units of the real power is watts, or mostly it is denoted as kilowatts as well. Okay, coming for this reactive power, volt, ampere, reactive. Okay, next coming for this apparent power, this is VA, volt, ampere. Okay, so why these are required here? So actually the power which we are going to generate is the real power. Okay, so because of the use of these type of elements, which we call it as the circuit elements, right, the inductor or capacitor, so because of the inclusion of these materials, then obviously the reactive power comes into picture. Okay, like for example, let me take the screen. Suppose this is a resistor. Okay, if the circuit consists of only pure resistor, there is no concept of reactive power. Only the real power exists there. Only the real power exists here. Okay, so I mean, so when we are going to supply voltage, the current drawn by this resistor is I, and it absorbs energy in the form of heat, that is I square R. So P equal to I square R. Whereas suppose if there is any inclusion of inductive element in the line, or any kind of appliances if you consider, so let it be L. Suppose if I am applying a voltage across this inductor and it is going to draw the current, so then what is this power absorbed? For time being, I'm mentioning the P. Okay, don't get confused, or else you can write it as Q as also. So the power absorbed by this inductive reactance is I square XL. Similarly, suppose if there is any capacitor, let it be XC, and the same, if I'm going to apply a voltage VC, okay, and it is about to draw the current, then what is the power absorbed by this capacitor reactance is I square XC. So this is how the power consumption here, and it is in the form of electromotive force, I mean EMF, and here it is electrostatic field. Okay, so that is its behavior. So basically we have three circuit elements, RLC, any of the appliance or any of the load, if we consider, like for example, refrigerator, air conditioner, or any electrical appliances, or any electrical gadgets if we consider, any of these fall under these categories. It may be resistor, it may be inductor, or it may be capacitor, or combination of any of those. Then reactive power comes into picture. So that is what I have mentioned in this description. So let me move to the next slide. Yes, I have given a small physical example here. So just we can, just a second. Okay. So I'm not considering about the type of brand or any company here. Let me take this physical example, that is a chips. Okay, a packet of chips. Just to understand what is the importance and what is the relation between these types of powers. Okay, a packet of chips here, and we know that, so all the stuff what we require, like the chips is deposited at the bottom. So this is the actual position where the exact quantity is required. Okay, so just we can or here, okay, so let it be here. Okay, so this area is the where chips are available, right? So this I can consider as active power. Okay, it may be watts or kilowatts, no issue, watts or kilowatts. Okay, so this is the exact thing what I require. I'm not bothered about the cover. Okay, I'm not bothered about the air which is locked here or which is packed here. Okay, so in order to maintain the freshness of the stuff here. Okay, next, what about this part? So there is no quantity exactly available here, but that is also required in order to maintain the freshness of this stuff. Okay, so that I am comparing with the reactive power, so which is not the actual work done. So to say that here we want the work to be done. Okay, so actual work done is real power, right? So this is of no use, but without this reactive power we cannot reach the real power. And what about this cover? I mean, which gives the exact size and the quantity of the element. Okay, I mean the appliances. Okay, if we consider with the physical example. Okay, so this is the apparent power VA. So which gives the exact size, and I mean we can call it as the rating. So the rating can be fixed or the capacity can be fixed based upon this VA. So that is the apparent power. Okay, so that is the relation of this real, reactive and apparent power. So already I have written these equations. P equal to, which is also called true power, which is also called active power, which is also called real power. So like this many terms are being used in order to determine this real power. Okay, so which is I square R, which is in the form of heat. Okay, if the circuit element is resistive, pure resistive. Okay, so next, coming for this reactive power. So if you denote the reactive power with Q, then which is equal to I square into X. So again, I'm letting you know, it may be I square XL. If suppose if it is a pure inductive, or if it is a pure capacitive, then it may be I square XC. And again, if you ask me what is the value of XL, it is 2 pi F into L. And what about XC? That is 1 by 2 pi FC. So where 2 pi is the constant, F is the fundamental frequency or the frequency of the current or voltage of that particular element. For example, if this is the inductor, okay, so and this is the current flowing through the inductor, and this is the voltage across the inductor. Okay, so this particular parameter, the voltage or the frequency or the current has a particular frequency. Okay, so there will be some alternating component which is flowing through this element. Okay, so that particular frequency defines this value. Okay, so and L is the value of that inductor, okay, which is in henries. And what about the units of this capacitor? It is in farads again. Okay, so done. Next, about the apparent power, it is I square into Z. So why Z comes into picture here again? So Z equal to So already we have discussed in the previous session. So z equal to root of r square plus x square. So again x may be combination of xl or xc or both. Okay. So z defines the impedance. So impedance represents the overall circuit uh, real and reactive components. Okay. So r represents the real component and x represents the reactive components. Okay. So that is about the introduction of this real, reactive and apparent power. So already this, I mean the relation of this real, reactive through the power triangle already been discussed. But anyhow, just in a short, I would like to give you. So from this is called as the power triangle. Just a second. So this is called as the power triangle. So it is a source of the right angle triangle there. So which is this part is called as the hypotenuse, and this is the opposite side. This is hypotenuse side, and this is the adjacent or base. Okay, so here this is S, this is P. Already here we have given P, Q, and S. Okay, so if you want to find out the magnitude of S, which is equal to root of P square plus Q square. So already I have said. So this is actually the imaginary component. This is the real component. This is real, and this is the imaginary. So basically, it will be root of p square plus j q whole square. So the value of j is -1. So hence it becomes root of p square plus q square. Okay, so that is the relation of apparent power, so which is useful for define the capacity or rating of the machine. In the same fashion, so we can find out the relation of impedance z, which is a combination of r plus j x. Okay, so again when I discuss with the relation, I mean when I discuss about the series and parallel connected circuit elements, then I can aware you about this xl xc series combination and parallel combination. Okay, so that's about the relation of real, reactive, and apparent power. So by this, what are our observations from real, reactive, and apparent power? So the actual power required is real power, and without reaching the reactive power, there is no concept of real power transfer. Okay, so reactive power helps in maintaining the real power transfer. So in a single point, we can remember. Okay, and again, so we cannot go for a pure resistive loads because 90% of our loadings are lagging loads, which is called as the inductive loads. Okay, so that is the dependency of this inductor and capacitors. Okay, so next we will move into the some basic laws in electrical systems, which are quite useful for us when we go with the further concepts. Okay, so Faraday's laws of electromagnetic induction. So I think we have studied few years back, right? Again, just will recall the only important things. Okay, so here if you observe this solenoid, so this is called as a basically a solenoid. Okay, so again if I go before this, if I start about this solenoid, so again we need to just recall the things of what is a magnet, I mean what do you mean by a permanent magnet, and what do you mean by electromagnet. So we have to just recall these two things. Okay, so permanent magnets, it is nothing but a permanent magnet. Okay, so this is an electromagnet. So we are going to create a magnetic field with the source of electricity. Okay, so just this is a simple solenoid, and we are going to provide certain windings here. Okay, so which acts as an electrical circuit there, and if we are going to power up, I mean if we are going to supply voltage here, so because of this closed circuit, it draws certain amount of current. So let us think like in this way. This is the direction of current. So what happens? So it is going to create a magnetic field here, which is the source, which is the cause for electromotive force. Okay, so or else we can call it as electromagnetic field. Actually the electromagnetic field is created here, which is creating certain force again, so we call it as an electromotive force. So this is the behavior and this is called as the electromagnetic field. Done? Right. So now as per Faraday's law, so what he is going to suggest here, if you look at the first statement, so it is directly, Faraday's law states that EMF is induced in a circuit which is directly proportional to the time rate of change of flux. Yeah. So it is directly proportional to the time rate of change of flux enclosed by the circuit. So before going for the statement, I can call it as a current carrying conductor is placed in a magnetic field. Okay. So I am a current carrying is placed in a magnetic field. Okay. So an EMF will be developed. Okay, so that EMF is depending upon, so the rate of change of flux, which we call it as d phi by dt. Actually it is E, the electromotive force or the EMF induced is directly proportional to rate of change of flux with respect to time. Okay, again if how when the flux is going to vary here, again we have to recall the sinusoidal waveform. Okay, let me take, yes, so this is the sinusoidal waveform, right? Okay, so this is the supplied voltage and the flux also follows the same waveform. Okay, so this is also a varying flux which we call it as d phi by dt. So it is an alternating flux. So d phi by dt represents there is a rate of change of flux with respect to time. So here this is the 0 degrees, from 0 to 90 it is maximum. Okay, from 90 to 180 again it is reducing, again from 180 to 270 it is maximum in opposite direction, and from 270 to 360 again it is getting reduced. So like this the flux is also continuously changing, so that is called as the d phi by dt, rate of change of flux with respect to time. Okay, so this happens only in the AC or the alternating component. Okay, so and it is proportional to EMF. Okay, how much it varies, I mean based on this variation of flux the EMF is induced. And again another parameter we need to consider, that is the number of turns. It depends upon the number of turns you are providing. So this is the number of turns, suppose this is a turn 1, 2, 3, 4, 5 and so on. It depends upon number of turns you provide for that circuit. Okay, so overall altogether we can call it as E is proportional to d phi by dt and E equal to n into d phi by dt. Okay, so this is about as per Faraday's laws of electromagnetic induction. And if you observe here there is a polarity minus, so that is because of the Lenz law. So what do you mean by Lenz law here? So effect opposes the cause. Effect opposes the cause. Suppose for example if we ask the students of some lower kindergarten or some senior KG or so like this, I mean very children, we are asking them to go through a line. Okay, some of the students get deviated or get distracted from the line. Okay, so that type of opposition is expected by default. Okay, because of its by nature or because of its behavior. Okay, the same way when we choose any conducting or semiconducting material, so when we are trying to apply voltage there, so obviously because of this flow of electrons, so uh, there may be some distractions. Okay, some opposition will be there expected, so that opposition represents the Lenz law effect. I mean the reaction is opposing the source, or the response is opposing the source. Okay, so effect opposes the cause. Okay, and of course we can ignore or we can avoid this polarity minus, because there will not be any EMF in minus. only always there will be a potential rise. There will not be a potential drop because we are creating the source here. So that is why it is being neglected. Okay, or you can just ignore this polarity. So directly you can write it as E equal to N into d phi by dt. So as per Faraday's law. Okay, so this is about the very important uh, a basic fundamental law. So that is the Faraday's law. So how the EMF is produced, and at the same time, what is the magnitude of the EMF? Magnitude in the sense the voltage magnitude or the potential difference, how much it is being developed in the circuit. So that is very important here because we need to run the appliance. We need to give a sufficient amount of voltage, or we need to enhance the sufficient amount of voltage there. Okay, so all these things can be done with the help of the fundamental law, that is Faraday's laws of electromagnetic induction. Next, already have discussed this Lenz law, effect opposes the cause. Okay, so just I'll complete this very fast. Okay, so this is the bar magnet, so which we know that two polarities will be the north pole and south pole. Okay, sorry, no, two poles, north pole and south pole will be there. So we know that the magnetic lines of force from north to south. Okay, so when see, if you observe this picture, I hope you can see, if we carry a conductor in this position, suppose, just let me do, yes, suppose you are holding a conductor in this position. Okay, so you are carrying like this. Suppose if you're carrying like a bottle, or if you are holding a stick in this direction, if this is the direction of current, and this will be the direction of magnetic field. Okay, so it is perpendicular. So that is the property of that material. So it is opposing. Okay, so that creates E equal to minus n into d phi by dt. Of course, we can neglect this. It is very negligible quantity. Okay, and we should not consider it as well. Okay, so that's about the Lenz law. Okay, if you hold based upon your direction of current, suppose this is the direction of current, and this will be the magnetic field. Okay, so this shows the, as per the Lenz law, we can find out the direction of current and direction of magnetic field. Okay, next coming to the left hand rule and right hand rule. So if you observe this diagram, so there is a north pole and south pole. So this is the north and this is the south. So we know that the magnetic lines of force from north to south pole, it travels. Okay, suppose if you are placing a conductor, so this is the conductor, I hope you can see here. Okay, so this is the conductor, it is placed on this magnetic field. So here one thing I would like to highlight is that either the current, I mean I can call it as, so the flux, actually the flux should be varying. So our major factor is that there should be a variable varying quantity or varying parameter or varying quantity. So that quantity may be current, that quantity may be flux. Any of these two quantities must be variable. So then only, so EMF will be developed there, and again, so the force will be developed. So these two are very important because one defines the motor rule, other defines the generator rule. Okay, let me show you this diagram. So this is the hand, if you consider this is the left hand. Okay, so the thumb indicates, here you can see the thumb indicates the force, direction of force. What is the force here? So I mean the conductor which is going to move here. Okay, so the force represents the direction of the conductor. Next, so this forefinger, or you call it as the first finger or forefinger, this forefinger represents the direction of magnetic flux. Okay, and so the middle finger represents the direction of current. So this is the phase displacement of these parameters F, B, I. So for easy remembrance, you can call it as CBI. Okay, so where F represents the force, B represents the magnetic flux, and I represents the current. So this is same for both left hand and as well as right hand. Again, both I am trying to cover here itself. Yes. So again, if you observe this, just ignore this thing. So something it was misplaced. Okay. Okay. So this is thumb. So thumb represents the force. Forefinger represents the flux. This is force. Direction of force can be denoted, and this represents the magnetic flux, which is denoted by B. Here it is denoted by F, and it represents current I. Okay, so the parameters remain same even for left hand rule or right hand rule. So the thing is that for motor we require force. We are not depending upon the EMF. I mean, how much voltage is induced, or how much I mean, what is the magnitude? All these things are not required. We are depending upon the direction as well as the how much of torque is produced. Actually, we are not going to torque discussion right now. So just understand that we require some kind force so that the conductor need to rotate. Okay. See. So as per this Biot-Savart's law, so B equal to mu naught I into I by 2 pi r. So mu naught represents the permeability. Okay. So I represent the direction of, sorry, the magnitude of current. So if you observe here, so I said already one varying quantity should be there. So that may be varying current or varying flux. So again, I'll just recall the things. Whenever a current carrying conductor is placed on a magnetic field, I repeat once again, whenever a current carrying conductor is placed on a magnetic field, a force is developed on the conductor, or a force is observed in the conductor, okay, or a force is induced in the conductor. So that rule we are using for to identify the parameters in the motor. Okay, and coming for this generator, whenever a current carrying conductor is placed in a magnetic field, an EMF is induced. Here we are bothered about the induced voltage, because in generator we need to produce the voltage, right? So the direction of the parameters like the force, magnetic flux, conductor, and the current, everything we can identify by using the left hand and right hand rule. So left hand is used for motor, right hand is used for generator. We need to remember that. Okay. So here if you observe these equations, okay, so the force developed here equal to, so mu naught I by 2 pi r. So mu naught is the permeability, which is around 0.99 for different kinds of materials. Okay, it depends upon the material what you choose there. So approximately most of the materials it may reach up to maximum 0.99 or 0.9298 such a way. Okay, and I represents the current flowing through the circuit. Here we need to remember that when the current is allowed in the circuit, when the circuit is closed, done. If the circuit remains open, so then what happens? The current remains zero and there will not be any flux produced. Okay, so the motor will not work. So definitely the circuit should be closed, then only the current will be flowing through this conductor. Okay, and here, so F equal to the force developed is, so BIL sine theta. So for, see, it is a rotating quantity, right? So suppose if it is starting from 0, 90, 270, and sorry, yeah, 90, 180, 270, 360 degrees. So like this continuously it will be rotating. So we know that for all the angles, so the force is not constant here. Okay, so of course the overall force should be maintained constant, but for different angles, suppose for example sine 0. So what is sine 0? It is 0. What about sine 90? It is 1. Okay, so like this the force also varies, depends upon the angle. If you want to know in terms of angle, at particular angle what is the force developed, so then we can use this equation. Okay, so here I represents the current flowing through the rotor circuit. So here it is I. Why I have written I2? In the sense, this is the secondary or the the rotor current. Okay, so we are much bothered about the current flowing through that particular element. So two parts will be there, basically stator and rotor there. So we are bothered about the rotor current, so which is the secondary current. So once I discuss with the DC machines and all, I will make you more familiar about this. Okay, just try to understand. These are the very fundamentals. Okay, so 2 pi r, where r represents the radius of that particular conductor. Okay, next, so this force, this equation gives the direction of force and as well as the force developed in this particular conductor. Okay, so what are the dependent parameters here? So magnetic flux, current flowing through that particular conductor, length of that particular conductor, and which angle, because continuously 360 degrees it will be rotating, right? Next, coming for this generator, so already we have discussed E equal to, so again just ignore this negative polarity because of the Lenz law. So again BLV, if you want in terms of angle you can write BLV sin theta, or else just if you want to know about the magnitude it is BLV. Okay, if we consider n equal to 1, if there are considered, let us consider only there is one term. Okay, or else we can use this n as it is. So it is started from E equal to n into d phi by dt. So directly you can use this equation if you find difficulty in this. Okay, so E equal to n into d phi by dt. So that's about the motor and generator rule. Next, we'll go with the Kirchhoff's voltage law and Kirchhoff's current law. So some of the people they pronounce it as Kirchhoff's voltage law and Kirchhoff's current law. So that is as per your convenience. So I can pronounce it as Kirchhoff's voltage law and Kirchhoff's current law, KVL and KCL. Okay. So just look at these diagrams. I made it very simple. So considering the internet sources. So so what about this KCL? So KCL already here I have given. So the statement is that the current flowing out of any node must be equal to the current flowing in. So we can call it as incoming currents is equal to outgoing currents. Okay, and again before that you may ask me, sir, what is a node? Okay, say a node is a point of connection of circuit elements. Again, if you ask me circuit elements, what are the circuit elements? So those are resistor, inductor, capacitor, voltage source, and current source. All these 5 components comes under circuit elements. The point of connection of these circuit elements can be termed as a node. Okay, so okay, so incoming currents is equal to outgoing. What do you mean by incoming here? So let us consider any node. I just have highlighted here. So this is a node. Okay, so this is a node. Here I can see a branch. So this is a branch. This is branch 1, branch 2, and this is a branch 2. So again, what do you mean by branch? So a branch represents the path of circuit elements. Okay, so sorry. Yeah, branch represents the path of element between two nodes, circuit elements between two nodes. A branch represents the path of circuit elements between two nodes. Okay, so this may be a voltage source, this may be a current source, this may be a resistor, inductor, or capacitor. Any of the elements may exist here. Okay, so here this is the point of contact, or this is a node. Okay, so here I have given the direction of current. So this is the downward direction. I consider it as an incoming for this node, and here certain element, suppose here in this branch 2 there may be a inductor or there may be a capacitor. Okay, so the direction of current I have given as in downward direction. Okay, so this I can consider it as outgoing. Okay, and this is also outgoing. Suppose the branch 3, which may be a resistor, inductor, or capacitor, or any other sources, voltage or current source. Okay, so the direction of current I have given as downward. So here for this particular node, so I1 is the incoming, and another two branches are there. So this is B1, this is B2, and this is B3. And what are the direction of currents of these two branches? These are currents in such a way, I2 and I3. So for this, if I want to apply KCL, so as per KCL, incoming currents is equal to outgoing currents. What are the incoming currents for this particular node? Let us call it as node X. Okay, so I1 equal to I2 plus I3. Okay, so as per KCL. Okay, so let us see further in the problems that how we are going to solve the problems and where it is being useful. But as of now, just understand that what in by KCL. So incoming currents is equal to outgoing currents in a node. Okay. Next, coming for this KVL, Kirchhoff's voltage law, KVL. Okay. So algebraic sum of just look at this statement here. Algebraic sum of the voltages around any closed path must be zero. So then this, so since it is a very fundamental and important statement, I'll write you a complete statement here. Algebraic sum of all branch voltages algebraic sum of all branch voltages around a closed path in a circuit is always zero at any instant of time. So this is what the exact KVL statement is. Algebraic sum of all branch voltages around a closed path in a circuit is always zero at any instant of time. So this we need to remember. Okay. So if you see these three branches, 1, 2, and 3. Okay, so these plus and minus represents the direction of the current here. Okay, so what a KVL statement is that the voltages, if you sum all these voltages of these branches, suppose three branches are here, if you add those all the branches, it should be equal to zero. That is V1 plus V2 plus V3 must be equal to 0. And another important factor is that we need to assign the polarities here, whether it is positive or negative. So that how we can identify. Suppose if you consider this is the direction, any direction you can consider. Only two directions will be there, one is clock or anti-clock. Okay. Suppose if you consider this direction. So if you start from V1, it is starting from minus to plus. So then I can call it as potential rise. Again, here, and it is entering to the next branch. And what about the polarities here? It is starting from minus to plus. So this is the direction. So again, there is a potential rise. And coming to the next branch element, it is going from plus to minus. So there is a potential drop. So I can use the polarity as minus is equal to 0 as per KVL. Okay. So this is what the statement of KVL and KCL. I hope we can discuss in the next class. Let's move to the discussion session.